Here's a nice little result that pops up every once in a while. Let's let n be a geometric random variable. Okay, counts the time till the first success. And then these x's are IID exponential lambdas. What this means is they're independent and identically distributed. That's what IID means. Okay, and they're independent and they have the same distribution. Okay, each one is distributed exponential with parameter lambda. That is, their mean is 1 over lambda. Okay, so these are exponentials. This is a geometric. What happens if you take a sum of these exponentials? Well, I know that the sum of if I just take a finite fixed sum of these guys, these independent identically distributed exponentials, that's gamma. I already know that. But what if I take a random number of terms in that sum? What if I let the number of these guys be exponentials? So it's sort of like, you have an exponential random variable that plays out, and then at the end of that time, you toss a die, okay? And depending on the outcome of that die, then you generate another one, another exponential. And then you toss a die again, and then you generate another exponential, and you keep on tossing the die and doing all this stuff until, say, you see a 6 for the first time. And maybe the first time you do that, then you generate one more exponential random variable and stop. Okay, so the number of terms in this sum is a random variable. It's a geometric number. This is a different kind of a thing. Right? So we can do this with moment generating functions. So what I'm going to do is just write down the moment generating function form for that random sum. Okay, and I'm going to hopefully show that this thing turns out to have the same form as the moment generating function for an exponential, but with parameter p lambda instead of lambda. Okay, so in fact, maybe at this point you want to stop the recording and try it yourself. That'd be a great thing to do, or stop anywhere along the way and get a sandwich, fuel up, try this out on your own. Right. K goes from 1 to n. Now, the first thing I'm going to do is I'm going to make use of that nice tower property. Remember the property that says that the expected value of a random variable, you can write it as the expected value of that random variable. Told you that was useful. Oops. Given. Now, at this point, when you go to use that tower property, you want to think to yourself, what kind of information would be useful? If I knew something here, what could I make use of this thing? Let's see. I guess, you know what? If I knew the number of terms in there, then this would be really helpful. Right? If I knew what n was. So yeah, and in fact, now I can write that this is just the expected value of, now if I know what n is, if I know this number, if it's like 5 or something, what's the expected value of all of this stuff? So it's going to be the moment generating function for a gamma, right? If n is fixed, if it's no longer random, then I've got a sum of exponentials. We've already established that that's gamma, right? So all of this stuff in here, all of this stuff is just the moment generating function, and I'm just looking this up in my book, right? T over lambda raised to the negative n, right? There we go. So now let's see. I still have this random variable here in this expectation. I know what this means. It says to, n is geometric, right? So I'm going to take 1 minus t over lambda raised to the negative k times the probability that n equals k. And k goes from 1 to infinity, right? K is my little dummy variable that represents my geometric random variable. Okay, so I'm taking the expected value. This is important to see it like this. It's the expected value of a function of its geometric random variable. And to carry that out, it's just the weighted average, right? You're averaging it against the probabilities for the random thing of all of this stuff, right? All right, so I think what I'll do now is I need to fill in that. I'm going to put this in the bottom, make this look a little easier for me to see it anyway. To the k. Now the probability that n equals k, that's p times 1 minus p to the k minus 1. Okay. Now I'm going to pull out the p, and I'm also going to pull out one of these factors so that I have all this stuff, so that every factor in here is raised to the same power of k minus 1. And I'm going to do it like that because I'm going to also want to change my starting index here. I want to start this summation with the 0, with k equals 0. So just pull this out here. I got a p over 1 minus t over lambda times the sum. K goes from 1 to infinity, 1 over 1 minus t over lambda raised to the k minus 1, right, because I pulled one of those out, and then times 1 minus p to the k minus 1. Now, I'm going to make a change and go like that, right? Now, I know that this stuff is bounded by 1, and what about this stuff? This stuff is also less than 1 for certain values of t, or at least, less than 1 in magnitude for certain values of t. So I know that in fact I can write that for certain values of t anyway, this will be 1 minus t over lambda, right? And then times 1 over 1 minus p over 1 minus t over lambda, right? See that? Because I'm summing from 0 to infinity, all of this stuff is bounded by 1, so the sum is 1 over 1 minus all of this stuff, right? Okay, this is a 1. Okay, all right, so what is that? Let's see, I've got a p in the top, and I'm going to multiply through the bottom by all this stuff. I get 1 minus t over lambda minus 1 plus p. Okay, so that's looking like p over p minus t over lambda, or if I divide the top and the bottom by p, I get 1 over 1 minus t over p lambda, which in fact, yeah, that's the moment generating function for an exponential with parameter p lambda.